Alright, Calculus Lesson 6, what we're going to do is we're actually going to bring together everything that we've done so far in differentiation. All the different techniques and rules that we've used to date, we're now going to put into practice. And in a way that I'm not actually going to tell you which rule to be using. That is something that you're going to have to learn on your own. So I'm going to go through a little flowchart that highlights the different methods to use, the different rules to use under the different circumstances. So we're going to work on finding out which rule to use and then executing on that. And we're going to do 6 pretty decent standard examples. And so I'm calling lesson 6 the art of differentiation. So my flowchart. When to use which rule? Now I've decided that let's start off with asking ourselves the question, will it easily combine? If it does expand or simplify easily enough, if that's a yes, then we're going to be using our basic law, which we know bring down the power minus 1 from the power, and with that all you need to make sure of is always convert into index form. And you can see that little ice cream there, that's vanilla. That's what I'm going to be referring to our basic differentiation as. It's plain, it's basic, it's vanilla. So we'll call it vanilla differentiation from now on. Or we may be using our chain rule, which we know as well. Bring down the power, minus 1 from the power, and then don't forget your chain, times by the derivative of the bracket. So that's if it easily combines. I'd probably suggest doing that. It may make life easier for you. If you don't see it like that, if you can't see it combining easily, so if it's a no to that answer, it means you've got two terms multiplying together that will not expand. They just don't mesh, they don't go together. If that is the case, you treat them as two separate terms and you use product rule. What about the other option, which is if they are dividing by each other? So you've got two terms that are dividing by each other that won't simplify. Remember, you can never split up the denominator, ever. You can split the numerator over the denominator, but you can never split the denominator. So if the denominator as a whole doesn't divide through by the numerator, it means it's not simplifiable. So you can't simplify it, in which case you've got to treat them as two separate terms again and use quotient rule. Those two rules should be familiar now. If they're not, go back and review the lessons on them. And that is our differentiation flowchart. That takes you through where you should be able to assess each question on its merits and decide which rule to use and when. But importantly, don't use this as a hard and fast rule, because often they're ones that are ambiguous as to whether it can combine. You know, sometimes you don't see straight away how easily it can combine, in which case you go with whatever suits you. There's often more than one way to do a differentiation question, as we will show. So let's begin. Calling it miscellaneous differentiation, because it could be anything. And I've included our little intimidator icon there, because all of these are tough and they should scare you when you first see them. But you just got to attack them step by step. First one. There you go, intimidator. 1 minus 4x squared all to the 4 over 1 minus 2x outside of 1 plus 2x. Now, first question to ask yourself, will it easily combine? Well, you look at it and there should be something in that that instinctively is nagging at you to expand, and that's the bottom. Because those two, 1 minus 2x, 1 plus 2x, you should recognize as conjugates. And conjugates multiply together to give you the difference of two squares. It's the first squared minus the second squared. So when you expand that out, because it is a yes, you'll get the top remains the same. The bottom, because they're conjugates, and as we just said, conjugates expand into difference of two squares. The first squared is 1 squared, which is 1, minus the second squared, so 2x all squared is 4x squared. So we have 1 minus 4x squared to the 4 over 1 minus 4x squared. And naturally, you should see that that will then simplify further. The 1 minus 4x squared on the bottom will cancel, and you'll be left with 1 minus 4x squared to the 3. Or you can think of it as the indices minus one another. 4 minus 1 is 3. Either way. And now we can actually differentiate it. So with a lot of these, more of the work is actually in getting to the point where you can differentiate as opposed to the differentiation itself. So now we can differentiate that. And how do we do it? You should recognize that as a chain rule. Alright, bring down the power, minus 1 from the power times by the derivative of the bracket or the chain. So that gives us by times by minus 8x. Tidy up your loose bits. So you get minus 24x into 1 minus 4x squared, all squared. And you can leave it like that. Perfect, nailed it, beautiful. Second one. Y equals 2 minus 3x squared over pi x. Again, intimidator. I'm especially doing it. So you should be intimidated. I'm throwing pi's and ugly equations in there to try and get you off your game. But just approach it the same way as you will from now on out. Ask yourself, will it easily combine? If you can see how it's done, then go for it. Say yes and work it through. With this one, you can split it up because fortunately the denominator is just one term. It's not a set of terms because you can never ever split up a denominator. You can, however, put the numerator over the entire denominator, and because it's just one term, you can do it in this set. And so you'll see how that's done. It's 2 over pi x minus 3x squared over pi x, which means we've got our basic or vanilla differentiation. But before that, let's just tidy it up. We've got that second term is 3x squared over pi x. Let's cancel out one of our x's from top and bottom, and we're left with 2 over pi x minus 3x over pi. Okay, now in order to do our basic or vanilla differentiation, we've now got to work with it in index form. The first one is not in index form because the x is on the bottom, so we need to bring that x up. How do we do that? We give it a negative index. If you're not sure of that, go review the lesson negative indices. But we bring that up, give it a negative index. And now we're ready to go. One of the most confusing parts here, though, is the 2 on pi and the 3 on pi in front of the x's. The important thing here is do not get intimidated by those. They are just numbers. And the numbers do not affect the differentiation in any way. So just do normal differentiation and times it by the numbers or the coefficients of the x's. To accentuate this point, I've put my little green circles around the x's, just to show you that that's the only thing you're worrying about. That's the only part that you're differentiating. The rest of the stuff is just numbers. So differentiate with respect to x and times it by the numbers after. To see what I mean, do the first term. So it's 2x to the negative 1 over pi. You bring down the power and minus 1 from the power. So bring down the minus 1, so it'll become minus 2 on pi, x to the negative 2, because you minus 1 from the power. And the second term, minus 3x on pi. Well, minus 3x on pi, minus 3 on pi is just a number. Pretend it was minus 3x. You wouldn't have a problem. Minus 3x would just become minus 3. So minus 3 on pi x is just minus 3 on pi. So hopefully that should make sense. It is intimidating when you have these numbers in front, these coefficients, particularly when they involve things like pi's. It does get confusing, but treat them just as numbers. So try not to let them creep into the difficulty and make it harder on yourself. Just treat it as a normal question. Now, alternatively, if you did not see how it could combine and split it up, you'd say no. In which case, it's a non-simplifiable 2 terms divide by one another. So what you would do is you'd use quotient. You can easily do this as well. So take the same question, write out your formula as you always do. I've just quickly done our chopping board there. U is 2 minus 3x squared, so U dash is minus 6x. V is pi x, so V dash is pi. And then I've just subbed them in. Sub it in the next step, I will expand it through and just tidy it up. So you get minus 6 pi x squared, and then I've timed the minus pi through into the minus 2, so it's minus 2 pi, and then the two negatives make a positive, so it becomes plus 3 pi x squared over pi x all squared. Okay, now we've got those common terms, the like terms, minus 6 pi x squared and the plus 3 pi x squared. Together, they'll add to give you minus 3 pi x squared minus 2 pi all over pi squared x squared. I've just expanded the denominator now from pi x all squared to pi squared x squared. Now let's take out a common factor on the numerator, which is going to be pi. That's the only thing common. We take that out. That'll then cancel top and bottom, and we are left with minus 3x squared minus 2 over pi x squared. That is absolutely the same as our other answer there. It's just in a different form. It's just our first answer was split across two numerators. It had a negative index. This one is a whole fraction. Same though. It really doesn't make a difference. You go with whichever method you find easier and whichever you see. Next one. Y equals x cubed times by the square root of 2 minus 3x. Again, scary looking because of the roots and the squares. But you say to yourself, will it easily combine? And you should see off the cuff that this isn't going anywhere. Those guys aren't on speaking terms. They do not connect. So, not expandable. It's a product rule. U is x cubed. V is root of 2 minus 3x. I'm going to just change that into 2 minus 3x to the half. Why? Because we always, in differentiation, we always work in index form. I can't find v dash using that root. I've got to have it in index form before I differentiate it. So let's just do u dash 3x squared, which should make sense. V dash, well, it's chain rule. So bring down the power, minus 1 from the power, and times by the derivative of the bracket. So bring down the half, minus 1 from the power, so half minus 1 is minus a half, and times by the derivative of the bracket, which is minus 3. So that leaves us with a real ugly looking number there. Minus 3 on 2 into 2 minus 3x to the negative half. Ugly, unattractive. You're not going to be enjoying these numbers, but just you've got to answer the question. It's going to reward you in terms of the number of marks. I can promise you that. So just write out your formula, sub them in their entirety. In the next step, we'll try to tidy it up. Wherever we can times through, we will. And in this case, only the x cubed and the minus 3 and 2 will times. So I'll just rewrite it nice and neat. As you know, time to take out the HCF. Bit of a tricky one, but you can see probably the 3x squared would go into both. And then you always want to take out your chain, as we've discussed, the 2 minus 3x part out. Here we've got to the half and to the negative half. Hopefully you remember from the last lesson when I said store it in the back of your mind. The negative index is the one you should take out as the HCF. That will help you. So we want to take out 3x squared into 2 minus 3x to the negative half out as our common factor. Now we've got to look how many times does that need to times in order to get that term. Well, it's just 1 2 minus 3x, and I say one of them because when you times that through, you add the indices, and minus a half plus 1 will give you a half as desired. So it's 2 minus 3x to the 1, and what do we have to times by in order to get that second term? Well, just 1 negative half and an x, so negative half x. Alright, that's the hard part. And then we just tidy it up. I'll just rewrite that out without the to the power of 1, and we'll fix that bracket up. So 3x minus half x, we can group them because they're like terms, so it'll be negative 3.5x or negative 7 on 2x. And there's the answer. Very happy with it, left like that. Not easy, but worth at least 3 or 4 marks. So it's juicy enough. Okay, let's try a fourth one. Root x minus 3x cubed over x squared. The obvious question we've got to ask ourselves every time now is, will it easily combine? In this case, you should be able to see that it will. And that's because the denominator is just the one term. So you can divide them both over the denominator. You can split up the numerator over the denominator. Remember, you can never split the denominator. So when it's one term, it's quite easy. When it's a couple terms is when it's harder to combine. So this one will relatively easily combine. Okay, you could do product rule, but it will get quite difficult. I can guarantee you that. So the easier way is to split it. But before we split it, let's just rewrite it all in index form, because you know that's how I like it, and you know you have to work in index form in order to do calculus, in order to differentiate. So we've got it in index form because root x is x to the half. Now we can split it. X to the half on x squared minus 3x cubed on x squared. Okay, now we just use index laws. So x to the half on x squared, you do a half minus 2. Because when you divide in things with the same base, you minus the powers. A half minus 2 is negative 1.5, or negative 3 on 2. So we get x to the negative 3 on 2. And with the other ones, we cancel out the minus 3x cubed and the x squared to leave us with just minus 3x. Okay, that is all still y. All we've done is simplify it. Okay, we haven't actually differentiated yet. That comes now. So as I mentioned earlier, a lot of the work is simply rearranging it and getting it into a position to differentiate, not the differentiating itself. Okay, differentiating now should be quite easy. It's now just vanilla. So all we do is bring down the power, minus 1 from the power. When we minus 1 from negative 3 on 2, we get minus 2.5, or minus 5 on 2. So our answer is minus 3 on 2, x to the negative 5 on 2, minus 3. If they do ask, and you know I like to add this on just as an additional, because if you can do this, great. They don't always require you to. I want you to be able to do it every time, if asked. So express it without fractional or negative indices. So first thing we've got to do is get rid of that negative. How do we get rid or give a negative? Is bring it up or take it down, respectively. So that x to the 5 on 2 we'll take down to go down with the 2. Then we've got to turn it from a fractional indice into a root. Remember, the roots grow at the bottom. So the 2 is the root. So it's the square root of x to the 5. So negative 3 on 2, root x to the 5 minus 3. And that's your answer. These are tough and these are ugly questions, but they are doable if you just take your time and you just follow our systems. Alright, next one. Differentiate f of x equals 3 over 2x minus 1. Looks simple enough. Now, first question we always ask ourselves with these differentiation questions, will it easily combine? As it happens, this one can actually be done a couple ways. So if you can see how it can combine, because this one can be, if you can see it, then do it that way. And the way that it can be combined is the whole denominator, remember, it can never be split, but the whole denominator can actually be brought up. Okay, and the only reason we can do that is because the top, the numerator, is a number. It's not an x. If it was an x, you'd have two x terms that didn't combine. But it's just a number, so we can technically bring that up. And what we do is we bring the whole thing up and give it a negative 1, because that's how we bring things up and down. We give or take away negatives. Now, that is just a chain rule. We therefore bring down the power, minus 1 from the power, and times by the derivative. So that leaves us with, when we tidy it up, minus 6 into 2x minus 1 to the power of negative 2. Okay, you can leave it like that. However, as I like to do with a lot of these questions, I want to make sure that your index laws and fractional and negative indices are good enough. And so they may ask you to express it without negative indices, in which case you've got to take that whole 2x minus 1 back down like it was before. And the way we take it down, just like the way we take it up, is using that negative indice. So we take it down and we take away the negative indice. So it is negative 6 over 2x minus 1 all squared. Perfect. However, as I said, there's a couple ways to do it. If you looked at that and said, will it easily combine, and you thought no, well, if that's the case, it's then going to be a quotient, because it's two terms that supposedly won't combine dividing by each other. So you write out your formula, you do your chopping board. I've just done it quickly there. U is 3, so the derivative is 0, and v is 2x minus 1, the derivative is 2. You then sub them into your formula, and you get that. You then tidy it up, which leaves you with minus 6 over 2x minus 1 all squared. Identical answer, two different ways. Alright, next one. Our final question. Differentiate y equals 2 minus x over 2 plus x all squared. Before we attack this, let's just separate that squared into the top squared and the bottom squared. As we could do with any squares or any square roots, you can just separate it into top and bottom. So we've got 2 minus x squared over 2 plus x all squared. Now we ask ourselves the question, will it easily combine? When you look at that, you can see that we're not obviously going to be able to split up the denominator, nor will it go into the numerator. Those are clearly not going to combine. It's not simplifiable. And so we've got a quotient rule. Some of you are probably thinking to expand out those brackets, expand out the squares. Now you could do that. It's obviously not going to help with simplifying it, but you could do that and use those expanded terms as your quotient rule. But ultimately it's just going to be more terms, which just means more work. So I would recommend just keeping them as is. Okay, chopping board. U is 2 minus x squared. V, 2 plus x squared. Now, U dash is going to be a chain rule. So bring down the power, minus 1 from the power, times by the derivative of the bracket. So when we tidy that up, it becomes minus 2 into 2 minus x. V, same deal. Chain rule. Bring it down, minus 1 from the power, times by the derivative. When we tidy that up, 2 into 2 plus x. So chopping board done. Now we write out our formula and we can just sub them in, as we've always done. Sub them all in. Now this looks confusing, and if you're not careful here, you're going to make a mistake with the expansions and the negatives. That's why you've got to sub them in their entirety in their own brackets, and then very, very carefully expand it and times through where you can. So when we tidy that up, we're going to get minus 2 into 2 minus x into 2 plus x all squared, minus 2 into 2 plus x, 2 minus x all squared, all over 2 plus x to the 4. Now that really sounds more difficult when I say it than it is when it's actually written there for you, but that should make sense. Next step with all of these, as you know, is to take out your HCF. So the minus 2, the 2 minus x, and the 2 plus x are our common factor. And when you look at it, what does that have to times by in order to get the first term over there? Just a 2 plus x. And what does it have to times by in order to get the second term? Just a 2 minus x. So when we clean up that bracket, the minus x and the plus x cancel, and we're left with minus 2 into 2 minus x into 2 plus x into 4. Tidy up the loose terms, the two numbers can times together, gives us minus 8 into 2 minus x, 2 plus x, all over 2 plus x to the 4. And you should be able to see that 2 plus x is common, top and bottom. We can actually just cancel that out. And it'll leave us with our final answer of minus 8 into 2 minus x all over 2 plus x cubed. And that's it. We've now, within those questions, had a go at pretty much every one of the types of differentiation that we've learned so far. We've also worked through our structures in terms of distinguishing exactly which rule to use and when, because that's really important. In the HSC, it's not going to tell you use this rule or use that rule. Often you're going to have to decide and execute it for yourself. And so this is a really good practice for you in terms of being able to do that.